Hello. This lecture will be the first lecture of hopefully a series of two lectures of the virtual laboratory experiment that we are going to conduct in 401 CHE 401 course. And I think it's a better idea instead of a lab manual in written format trying to explain a virtual experiment compared to this video, in which I'll try to explain the virtual experiment, showing you how it is done, how we can visualize it, how we can make the best out of this. So let me just dive into the topic, and let's see. I'm going to share my whole screen because I'm going to be talking about a large number of stuff. So, okay, let me start with our virtual experiment, the architecture of our virtual experiment. The architecture of our virtual experiment will consist of two tanks in series, one on top of the other one. And there is going to be water coming through this type, through this source feed, I may say. Then this rectangular tank will start filling, and until it is, well, you can I hope you can read the water height here in centimeters. Until it reaches 4 centimeters, there is not going to be any outlet from this left hand side pump. This is supposed to be a pump, so pump will be off until a height of 5 centimeters is reached. And then after we reach 5 centimeters and we extend this, then the pulp will start displacing water from this tank at a constant flow rate which we are going to determine. And all this time, as you can see, there is a hole in the first tank. And in this tank, there is going to be a pipe connected to this first tank. And this pipe is going to be pretty much is going to have a small diameter compared to this tank. The reason, or my emphasis will be clear in a couple of minutes, I guess. And through this pipe, due to gravity and due to the pressure of water in this tank, due to its height, which is going to be filled in a couple of minutes, I hope we are going to see some water or something which looks like water. There's going to be water going out through this pipe, which is going to fill this tank. And this second tank, which is actually a narrower rectangular tank, is going to be is going to contain a single hole at its bottom. And unlike the pipe here, there's going to be just a single hole here. And to give you an idea about the dimensions of the tank, how large are these tanks, I have found this video on YouTube, and you may visualize the largeness, the dimensions of the tank similar to this one. Kind of, well, it's 40 centimeters. Its height, of course, is going to be much smaller to this one. It's going to maybe half of this tank, right? But it's going to be the maximum volume that we are going to be using. So we may be using this whole tank, but we are going to be only using 40 centimeters of that. The cross-sectional area is pretty much similar that I've used in the models that you will not be seeing. We are just going to be simulating the whole thing. And the two tanks in series may be visualized in real dimensions and also compare with the dimension of this guy, the height of this guy. So these two tanks will be, when you put on top of each other, it's going to be kind of or close to a human size or a height of a person, or maybe slightly exceeds that or slightly lower than that. Well, actually, well, maybe the most important difference is going to be that long pipe here. This pipe is going to be, well, actually, I forgot about the exact length here, but it's going to be, I think, a couple of meters, if I recall correctly. So and it's going to be very narrow, as I said, compared to this tank, a very small opening. There's going to be a pipe. So why do I emphasize this so much? Because they are going to all determine the dynamics of the process. I want you to visualize or to get a feeling of the process as much as we can. So this is basically what the process will look like. Let me try to talk about the whole thing here. I have written, taken a couple of notes, and I know that you find my writing awful. You are right for that, but actually, it would take for me to write to prepare a PowerPoint slide a very long time. I didn't have that much time, and I was a little bit. I didn't feel very good. Anyway, so I prepared a couple of notes. Hopefully, I'll be talking about them. So I think it's going to be somewhat useful. So basically, we can put the whole thing into two dimensions in this perspective. So the first tank here, the second tank here, and our process or control variable will be the height of the second tank here. So basically, we are going to be interested in the water height in the second tank. This is going to be an important point. So the first tank is just going to be a process or a unit which is used to reach the second tank. But the important point here, the manipulated variable here is going to be the outlet of this pump here, the flow rate. So it's going to be this pump that we are going to regulate or manipulate in order to control the water level in the second tank. So here we are not directly interested in the level of the first tank, which we may call with H prime. But we should realize that what is going on will be in terms of physical process, the first tank will start filling, and then we are going to be taking out some water. So if you take out at a higher water flow rate, then H1 will be lower here. That's the important thing. The H1 will be lower. Lower H1 prime or H prime means a lower pressure here due to its height. Therefore, there's going to be lower pressure at this end, right? Entrance to the pipe. And therefore, the outlet flow rate through the pipe will be smaller. So therefore, there's going to be less water coming here. So how we can manipulate or how we can relate the manipulated variable to controlled variable is by this way. As you can see, it's pretty much, you may say, an indirect way of pairing these two. So you increase or decrease, you increase the manipulated variable, which is going to affect the, when you increase the outlet flow rate, the water level is going to decrease, which is going to decrease the velocity here, the inlet velocity, therefore the outlet velocity, therefore the water level will decrease here. So increase the manipulated variable, decrease H here. There's going to be a inverse relationship between those two, and it's going to be pretty much indirect. That's the mechanism of this system. Well, let me talk about whether this is a realistic pairing. Actually, for control purposes, this is not a very realistic pairing. What do I mean by that? Well, the first thing is that in process control, process safety is almost the very first fundamental issue here. So your equipment should not be destroyed, I may say, in the most non-engineering way. So here the problematic points may be the overflow of the first and the overflow of the second tank. When you control a process like this, please note that we would not be controlling H1 here. The water level H1 is not controlled. We are controlling H here, but we let just H prime loose. And this is from a process control point of view, this is unacceptable because the water level in the first tank may cause an overflow or the first tank may be drained. Well, actually, we got a kind of control mechanism here to prevent this from draining, because as I said previously, when water height when water height is less than 4, this pump, this manipulated variable will be automatically closed. So that's a good safety control mechanism built in there. However, I have not on purpose built anything to prevent the overflow of this first tank, so that you see that this is not a very good control. And the second problem of this one is, so in a real life case, we would be always controlling H1 to prevent its overflow. you would connect, very probably you would connect u to this h prime. That's one case here. And the second point here is a more mathematical issue. In real life, we also would like to connect the manipulated and controlled variables for desirable control. We would like the time constant between those two variables as small as it can be, which means in practical terms, there is little time lag between the input or the manipulated variable and the controlled variable. That's one issue, because actually if you just change the manipulated variable and very long time afterwards there's going to be a change in controlled variable, this is not something that you desire. You would like to obtain as immediate a response as possible. And here, as I tried to previously explain, the relation between u and h is pretty much long, because u affects h prime would affect the velocity here, velocity will affect the inlet velocity, which is going to affect h here. So it's going to be a pretty much, well, you may assume that each of these relations are first order processes, so there's going to be, we are adding lags here, and it's not a very good idea to realize such a control scheme. Now, another point I would like to talk about is related with modeling issue. I don't know whether we have covered something like this in any of the lectures, but instead of a hole, I put a pipe here. So what's the big deal, you may say? Now, you may visualize this book because you might have experienced this idea. You might have experienced this in real life. Now, when you have a tank and just a hole here, we can assume here the velocity, outlet velocity, is going to be directly equal to something, a constant times square root of h, or sometimes you can linearize it to an h value. But the point is, whenever h is equal to some value, u is directly equal to some multiple of a function of h. So actually, there, as you can see, this is an algebraic equation. This is not a differential equation between u and h. However, in real life, we usually know that velocity builds up. Even at the same height value, first velocity is slow, then it's going to get a larger value. It is because a more realistic way of thinking about the process, if there's a pipe here, and especially if this is a thin pipe. Why do I emphasize this thin pipe? Because in a thin pipe, there is going to be a high friction due to the small radius. Now, at a certain height value, the velocity here will not be directly equal to this value. Here, actually, velocity will be determined due to the pressure difference between the two ends. So here, what we are going to do is, I'm not going to go into the details of the mathematical model, but understanding the mathematical model is an important step in understanding the dynamics of the process, the causes for some time lags. And the reason for time lag is, when you put a thin pipe, you are going to have an additional resistance to this process for the outlet. So the outlet velocity will not be equal to, is going to be equal to some alpha times square root of h, but u is going to be determined by an additional differential equation. And this differential equation is written for this pipe here. So the left-hand side pressure is going to be, call it P bottom, and P bottom is going to be atmospheric pressure plus the height of the water here, minus pressure at this point. So it's going to be pressure air, right? So it's going to be just the pressure of the water height in this tank, and there's going to be, it's going to be the net pressure inside here, and there it is going to be also the frictional loss, which is related to velocity or velocity square. So there's going to be an additional differential equation here. Well, maybe the details are not important, but the understanding that additional mechanism or the reason for an additional lag is important to understand the process. Why then when you change the outlet velocity here, by the way, u is reserved, or I try to reserve it for manipulated variable. V is supposed to be reserved for velocity, but I think I somehow mess up with velocity and u. I have written here everything in terms of u. They should have been v velocity, of course. I'm talking about the velocity here. So this is manipulated variable. This is velocity, outlet velocity from the tank. So outlet velocity from the tank is going to be a function of time even at the same height value. So it's going to be another first order, at least a first order process. Actually, if we have v square in, and we have v square in our friction equation, right? Go to Fanning friction factor in design of fluid mechanics courses. You are going to see that it's going to be a nonlinear differential equation, and there is also nonlinearity buried here. Okay. Anyway, so why do am I talking about that? That pairing between u, which is the outlet velocity, and the height of the second tank is a kind of poor pairing. So in a real life, what we would do, as I said previously, we would pair u with h. As you can see, there is a direct relation between those two. So there's a first order relation, maybe better to say that, but direct is a more less mathematical term, but I think you get the idea. So when we would like to control the water height here, it's a better idea to put another pump here at the outlet and adjust the outlet flow rate as the manipulated variable and the control the H value. That would be a more realistic, which would satisfy both conditions, because the outlet velocity here is also in the first order differential equation related with H. Therefore, the relation between them will be fast. Otherwise, as the order of the differential equations get higher, the effective time constant or the leg of the process between manipulated variable and the controlled variable will be larger, which we do not want. So that is a poor pairing. That is not an ideal control case, but just for the sake of this virtual experiment, take it as it is. I wanted to see a couple of points here, how things are related, how processes are connected to each other. So as I said, also this would be the case. However, in some cases, the optimal control architecture, which I try to talk about, well, optimal in quotation marks, because we haven't solved any question, any optimization function or anything like that, may not be possible to realize. In some cases, maybe this may be a poor pairing, but in many cases, the best pairing may not be realizable due to economical reasons, due to safety, or maybe the process is designed in that fashion. So there are not much that you can do. So there may be other problems. For instance, one may say that why not put the manipulated, use this as the manipulated variable for the first tank, as the feed. That's a very good idea in terms of differential equation. There's a probably a very close to a first order relation between those two variables, manipulate variable and process variable. On the other hand, now in this question, I have assumed that this inlet is actually from an upstream process. So we have other tanks or distillation columns, blah, blah, blah. And at the end, from a distillation column, from the bottom product or whatever, then there is a stream which comes into this tank. And let's say that you are responsible only from this process. Therefore, you cannot change this inlet value, because this comes from the upstream, or this comes from the upstream process, as I said. Therefore, you are not responsible for that. You have to accept what it comes. Therefore, from this unit's perspective, this is going to be a disturbance. You cannot change this value. So that is one interesting point. You probably thought maybe think disturbance is a bad thing or something undesirable, whatever. Well, the thing is, this disturbance is something which is going to change the H value, the process or the controlled variable, but it is independent of our manipulated variable, or we cannot manipulate it. That is the idea of the disturbance. So for this case, the architecture of the process itself, how it is designed, prevents us taking any variable as the manipulated variable, as our variable, which we can change. Impossible. So there's not much we can do about that. So there's also that constraint. Okay, so the process specification. This is somewhat like design, but there's both the okay, the similar part to the design part. We know that the disturbance here is going to be equal to 2.05 liters per second. So the inlet here to this tank is designed to be equal to running at 2.05 liters per second. Well, in your experiment, while you are conducting the virtual experiment with your assistant, you are going to be taking this value as 2.0 liters per second. Why am I using 2.05 liters per second? Because I'm going to show you a couple of calculations and things like that. I don't want you to copy or take all of these calculations or parameter values exactly and apply it to your own. So I've changed this value slightly so that the results are the general idea is still going to be applicable, but the numbers that you are going to be using, the parameter values, blah, blah, whatever, they are going to be changed. So here, let's say these are the design conditions. As I said, for my in this lecture, we expect the disturbance to be equal to 2.05 liters per second. On the other hand, as you can see, this is almost equal to, because unlike the exact value for which we are going to be taking this value, we are going to be applying some fluctuations to this disturbance inlet value, as you are going to see. Let's continue. We expect that we would like to run the process at a steady state value of 21.7 centimeters. What do I mean by that? I'm talking about this second tank here. We are going to run this process somewhere here, 21.7 centimeters, somewhere between 20 and 22, very close to 22. Oh, by the way, how are we going to read this? These darker lines are well, I try to give a three-dimensional kind of visual perspective. So this is the front part, this is the side part, this is another side part, and this is the back part of the whole thing, if you can imagine what's going on. Anyways, in a couple of minutes, I hope we are going to be filling water, so it's going to be more clear. So here we are going to be operating this 21.7 centimeters, and to obtain the steady state value, we need to be applying an outlet water flow rate of 1 liter per second from the first tank. That's great. So these are the steady state conditions that we are going to be operating, but that's not all. During the operation, we are going to be making changes to the process. For some reason, for market demand, for whatever, we are going to be changing this H value, steady state value, from 21 centimeter maybe to something between 10 to 26 centimeters. And that's where process control, to be more specific, servo process control will come into role. If that was the only condition, we would not be needing a process controller. Well, of course, disturbance is also the case, but take it as constant as it can be. If we would not be changing the set point of the process, which is the steady state height value of the second tank, we would not be needing a controller. So on the other hand, during the operation, from time to time, I would say that, okay, now we need water at 15 centimeter level. Well, of course, for this specific process, what may mean, probably it doesn't mean very much, but in real processes, they are going to correspond to more realistic variables like concentration, outlet concentration, temperature, blah, blah. So I think you can easily convert to a more realistic setting. So at any instant, we should be able to change this 21.7 to any value between those two. And from that point on, then you you would like to make other changes. So from 21.7 to maybe 15, then we are going to run 15 centimeters for a time. Then we would like to change it to 25 centimeters or 10 centimeters, then run for a while. And we would like this procedure to go over the whole time, operation time, as long as the process lasts. And we would like an automatic controller which enables us to do that. So what do I mean by that? We are just going to give the set point here for the first tank. We are going to say is let it be 15 centimeters, and the process itself, by adjusting the U value using the PI control that we are going to be using, is going to bring the process to that 15 centimeters. Then we are going to be giving this a 25 centimeters, and the process will again bring it to 25 centimeters, and it will go like this. This is the general idea of the whole experiment.